Good morning class, Sairam. Today we are going to study Lorentz magnetic force. According to this, if we have any charged particle say plus q, and if this charged particle is running with some velocity say small v in any given magnetic field, then some force will act on that charged particle, and this force is magnetic force. And magnitude of this magnetic force, or you can say the complete force, is given by following expression, that is qv cross b, where v is your velocity of charged particle and this capital B is magnetic field. We can calculate its direction also by vector law, and it will be written as qvb sin theta n cap, where n cap is your direction of magnetic force, and this theta will be angle between velocity vector and magnetic field vector. So we have some special case also. For example, if your charge is at rest, means its velocity is 0. Suppose magnetic field is given but charge is not running. In that case, your magnetic force will become 0, because if you will put here v equal to 0, your answer will come out to be 0. So a stationary charge in a magnetic field does not experience any force. This we can conclude. If your charged particle having its velocity with angle theta, you can say, and theta is 0 degree or 180 degree, where theta is angle of velocity vector with magnetic field. So in that case also your charged particle will move parallel or anti-parallel, and in this case also your magnetic force will be 0. Why it will be 0? Because if you will put here sin 180 or sin 0, your answer will come out again 0. Now we have next case when theta is 90 degree. In that case we can say that charged particle will experience maximum force, and this force will make the charged particle to move on a circular path. Magnitude of this force will be qvb, because sin theta here will become sin 90 and it will be equal to 1. Then direction of this force can be calculated by Fleming's left hand rule. So what is it? You have to stretch your thumb, your first finger and second finger in this way that all make 90 degree angle with each other. If the central finger, forefinger and thumb of left hand are stretched mutually perpendicular to each other, and central finger point to current, four fingers point to magnetic field, then thumb will point towards the direction of force. Now suppose if we have electric field as well as magnetic field, in that case how much force will act on charged particle? Okay, that force will be F equal to QE plus QV cross B, and this force will become Q, take Q common, you will get E plus V cross B. Next we have force on a current carrying conductor. Now suppose your conductor is carrying some amount of current, and here in x direction you can say magnetic field is acting. Okay, in that case the force experienced by each electron in the conductor will be how much? That will be F equal to minus E, because this is amount of charge, that is Q, and V cross B. Here you have to understand that velocity of electron will be taken as Vd, which is drift velocity. Okay, so if suppose you have n number of electron, or n is the number density of electron, in that case total number of electron will be equal to small n into A into L. Okay, and if you will multiply number density by volume, then this will be equal to capital N. Now force experienced by the electron in dl length, that force will be NAdl that is small q, okay, number of electron including minus e, it will become small q, and Vd cross B, okay, or V cross B. This will result in following expression. From here you can say that this NeaVd, this becomes your current. This portion we have already done in current electricity, that NeaVd is called current. So from here we can say our force will be IdL cross B, or if you will integrate it, you will get force on whole wire, and that force will become IL cross B. If we want to write its magnitude only, then we will write ILB sin theta. Next we have force between two parallel infinite long current carrying conductors, or you can say you have two wires, say wire 1 and wire 2, and both are up to infinity, means they are placed close to each other, and this is small r. So force acting on RS due to the current I2. Now try to understand, in the first wire I1 current is flowing, in the second wire I2 current is flowing. Okay, in that case this wire will generate magnetic field towards itself like this way, and the second wire will experience some amount of force, that is F21. Why? Because it is carrying some current I2 and it is placed in the magnetic field of some other wire, so it will experience some force F21, and that F21 will be given by mu naught upon 2 pi I1 upon R I2L sin 90, or you can say this is nothing but your ILB formula. So from here we can get, if you will resolve this, you will get F21 equal to mu naught upon 2 pi I1 I2 upon R multiply by L. So for per unit length we can say our force will become mu naught I1 I2 by 2 pi R only. Okay, this will become F by L for per unit length. Now we can conclude one more result, that if in wire number 1 your I1 current is flowing in forward direction or in this direction, and I2 current also has same direction, then this force on second wire will be towards minus I. Similarly, force on the first wire will be towards plus I. Means if they are carrying current in same direction, in that case both wire attract each other. However, if your first wire is carrying current in forward direction but second wire in reverse direction, in that case both wire will repel each other. Okay. This can also be concluded by Fleming's left hand rule. Now we have next topic, that is definition of ampere. What is 1 ampere? So we know that force per unit length of wire is given by mu naught I1 I2 upon 2 pi R, and this is Newton per meter because we are talking about force per meter length. Now if you place I1 equal to I2 equal to 1 ampere and R equal to 1 meter, that is distance between two wires, then force will become 2 into 10 raised to the power minus 7. By calculation you can get it. So 1 ampere is dead current if passed in each of two parallel conductor of infinite length and placed 1 meter apart in vacuum, which may cause conductors to experience of 2 into 10 raised to the power minus 7 Newton per meter of length of the conductor. Means 1 ampere is that amount of current by which your wire will get attracted towards each other by this much force, that is 2 into 10 raised to the power minus 7 Newton. Now next thing we have how to represent of magnetic field due to parallel currents. Now suppose if in wire number 1 your current is flowing in this direction, due to this wire your magnetic field line will be in a closed loop, and due to the second wire your magnetic field line will be like this. If we will combine both the thing, means we are talking about combined magnetic field, so we will get this perimeter, okay, or this shape will represent your magnetic field. Now if your current is moving in opposite direction, then we can say that these magnetic field line can be drawn like this. Means at the center it is moving like this way, okay, like moving away from each other, and it is making a small encircle as current carrying wire makes magnetic field line around itself. Now we have next thing, that is called torque experienced by current carrying loop. Now try to think, we have one loop that is PS RQ, or you can say PQ RS. So in this loop some current I is flowing from S to P. This is the direction of current, and then it is going from P to Q, and then like this way, and then like this way. And let theta is the angle made by the plane of the loop and the direction of magnetic field. Now suppose this is the magnetic field I direction, and this is the loop making angle theta. As you can see here, this is your angle theta. In that case, force on SP branch, if we talk about this branch, that is S to P, then this force FSP will be towards J direction. Why? Because we have to apply F equal to I L cross B. So by vector law we can say that L cross B will result the direction of force in J direction, or you can say in J cap direction, like this one. Similarly, we can say that force on the opposite branch will be in QR direction. Again, this can be determined by a formula, that is F equal to I L cross B, and L is length of QR. Okay, so cross B. So if you will solve this by vector law, you will get direction of force in minus J direction. So these two forces will cancel out by each other, FQR and FSP. Now we will get only two forces which are useful for us, which is FRS. FRS means force on RS branch, means on this branch. And second is force on PQ branch, means this one. So we can say that here force on SP, first of all we will talk about SP, that is ILV sin theta, and then force on QR means this bottom one. This expression will also be IBV sin theta. Okay, and as I told you that they will cancel out each other, so net force will be 0 along y-axis. Now we have only forces which are useful for us, that is FPQ and FRS. Okay, so here it is mentioned in form of expression that FPQ will be ILB sin 90. Why? Because this angle between length vector and magnetic field vector is 90 degree. You can see this branch. Let me highlight it for you. This branch, you can see its direction is plus J cap and magnetic field is towards plus I cap. So your angle between both the physical quantities will be 90 degree. So here it is mentioned that is 90 degree. So our answer will be ILB. And from here we can say that our expression for torque will be force multiplied by PN branch, or length of PN branch. So this force FPQ is ILB and length of PN, that will be B cos theta. Now try to understand length of PN. Means we are talking about this perpendicular length, this branch PN. So if this is your B, hypotenuse B, then its projection will be B cos theta. So from here we can express that torque is ILB cos theta and L into B. Okay, this L into B will be how much? Or it will be what? It will be area of loop, because area of rectangle we know length into breadth. Okay, So this will become A, capital A means area of loop, and it will become IAB cos theta. So suppose if we have one more turn, okay, if we have one more turn of coil, then we can use capital N, where N will be number of turns. So total torque will be NIAB cos theta. Now try to understand, if we have one more angle, say phi, and this phi you can see in the diagram. Now suppose here, if this phi is the angle between normal to the coil and the direction of the magnetic field. So this angle, it is saying that, suppose this is your normal line, normal to the coil, and this angle is phi, that is angle made with magnetic field, and suppose this angle is theta. Now we know that if this angle is phi, and remember this line is in space, okay, this is in air, because this is making 90 degree with the surface of the coil, then this angle is phi, and this line, as I told you, this is making 90 degree angle, and this one we are saying phi, so this remaining one will be 90 minus this angle phi, and this we have considered theta. So here we can write that theta and 90 minus phi both are same angle by corresponding. Okay. So from here we can write that tau equal to IAB cos 90 minus phi, because we have replaced this value of theta by 90 minus phi, and it makes sin phi. So expression for torque comes out to be NIAB sin phi. Okay. So here one note is given that one must be careful in using the formula in terms of cos or sin, because it depends on the angle taken, whether with the plane of the coil or normal to the coil. Means you have to remember which angle is given, or in data of the question you have to remember which angle it's given. It is given phi or it is given theta. In terms of that only you will use either cos phi, cos theta, or either you can use sin phi. However, both are correct, but you have to keep in mind that which angle is given. Then we have expression for torque in vector form. We know that torque is given by NIAB sin phi. Okay, and torque is a vector quantity, so its direction will be n cap, and n cap will be unit vector between area vector and magnetic field vector. Why? Because it was only mentioned at NIAB sin phi. Okay, so this angle, or you can write sin phi, so this angle is between first vector and second vector, and I into A, this term is called magnetic moment. Okay, remember this is called what? Magnetic moment. So we can denote it by M, or magnetic dipole moment, you can also say this one also. So both are correct. Also one more thing is given, it depends on from where we are observing our coil. If we are observing our coil from top, okay, then it may look that it is moving in anti-clockwise direction, and if you will look it from here, from the bottom, then it will look like it is moving in clockwise direction. So it depends on from where we are observing the rotating coil. Now torque acts in upward direction along the dotted line according to the Maxwell's screw rule. So here you have to understand what is the Maxwell's screw rule. Suppose if you are applying your rotating force in this direction, okay, in that case this screw will move in anti-clockwise direction, because you are applying a rotating force in this direction. So it will come out, you are opening the screw, and the direction of motion of screw, that is plus j cap, that will represent direction of torque. Now we will talk about when torque will be maximum. Now remember, if phi equal to 0, then we can say that value of sin phi will become 0. That means our torque will be minimum. Okay, this torque will be minimum. Now if we use phi equal to 90 degree, in that case our torque, that is having expression of sin phi, means it will give the maximum value of torque, that is sin 90 equal to 1, and its maximum value is NIAV, where N is your number of turn, you know it, I is the amount of current, A is the area of loop, okay, and B is the amount of magnetic field. Now unit of magnetic field we already know, that is Tesla, and current is measured in ampere, okay, and unit of torque is Newton meter.